Can start?
Yeah.
Dear all, welcome to the Classical and Quantum Statistical Physics seminar. Today our speaker is Dr. Alexander Lopez. He did his PhD in 2007 from Venezuela, and then he did 2 years of postdoc in Venezuela itself, and then he went to University of Riesenberg in Germany for a postdoc of 4 years, and then he went to Ecuador as a postdoc, and where he is still working as an assistant professor. Today, the title of his talk is Photoinduced Electronic Properties in Low-Dimensional Systems. Alex?
Thank you. Thank you. Thank you very much. So, also it's a pleasure. The first time I'm in Guadalajara. It's not the first time in Mexico, but here in Guadalajara is my first time. I thank you all for being here. Soham for the invitation. Thomas, yesterday I saw a bit of the culture here, so it was really a nice welcome. So I really appreciate it. I'm going to talk about some recent models we have been dealing with in the recent years. And so the main idea of the talk is to try to engineer the physical properties of systems by either introducing electromagnetic radiation or by using time-dependent gate voltages in order to see how, by tuning the parameters, you can induce different phases in these systems. When I talk about phases, I'm talking about either you have a metallic phase, semiconducting, or insulating phase in a given material. So the response of the material, how it can be accessed or modified by this modulation effect. So before anything, so I have to thank the people I've been working with. So this is not my work alone. It's collaboration of several people who are describing this in this slide, but I think pictures speak better about what we are. So there are some youngsters. So Carla was with us doing her undergrad thesis. Gabriel is doing master thesis finishing now. Jose is one of the assistants at the lab. So these are the youngsters, and Esther is a young professor collaborator from Venezuela who is now working with us in Ecuador. And Solmar and Benjamin. So all of these, except the two of them, are from Venezuela. So they are Ecuadorians. And Benjamin is in Canada now, and Solmar is in Germany. And the older people, so here I am, of course, because although people say, don't believe me that I'm 51, so I'm 51 years old. So with Francisco, he's from Ensenada, from UNAM, the CENI. Bertrand is in France. Ernesto was my PhD advisor from Venezuela. He's now working also in Ecuador. And John, as Sohan said in the presentation, was my postdoc advisor. And with Rafael Molina, we have a collaboration. He's from Madrid, from CSIC. So this is essentially work I've been doing with these guys the recent years. Before delving into the technical details, I would like to briefly tell you where I come from. Not originally, I'm from Colombia, but the city I'm now is in Ecuador, is Guayaquil. So we have heard about Galapagos, the Galapagos Islands, because of the turtles, the big turtles. But there are also some hallmarks in Ecuador, like the pottery in Otavalo, the place I was telling you about. Many volcanoes. So here you have some volcanoes, which make the landscape when you arrive in Quito very beautiful. You see all these volcanoes around you. And this is called Pailón del Diablo. It's a natural cascade, so you can walk through these places. It's very nice, and you feel the power of water following close to you, but it's safe to do it, I hope. I was there. So very quickly, I show you the map of Ecuador. So you have 4 regions. This is the coast, the Andes, and the Amazonia, plus the Galapagos here. So these are the 4 regions. It's a very close, it's a very small country, 80 million people. So Mexico City, more or less, scale. So there is no physics program in our university. This is the the city of Guayaquil. And this is the campus of our university. It's a small university. It's a Polytechnic University. We don't have a physics program over there. There are like about 11K engineering students in this university, and we are trying to somehow motivate the idea that a physics program would be a good idea, physics licenciatura for many students who are interested in physics there. Okay, so now let's talk about business. So essentially, after this brief non-technical introduction, I would like to delve into what we are interested in is to present the motivation for the work, why we are doing this, what is the purpose of that. Then some models that we have been dealing with in the recent years. What is the ongoing work, what we'd like to do, and maybe to motivate some future collaboration with some of you. And then the outlook of the presentation. If I'm being too fast, or if you want to interrupt me, please feel free to do it at any time. I think it's better if we just simply interact and not going through the slides and simply just getting the information very quick and not stopping to discuss something about it. So for the introduction, I'd like to say what essentially is the aim of this presentation, what I would like to convey to you, that which kind of what you should expect from this talk. So which kind of questions we have to address in this presentation. So we focus on spin systems, but not from the point of view of the statistical physics that we were discussing in the afternoon, but more in the context of spin systems that are not interacting with each other, but with a given environment. So essentially you have the spin degree of freedom that can connect, or that can somehow be coupled to the environment. So via spin orbit interaction, so the orbit of the particles get coupled to the spin degree of freedom of charged particles that are around. For instance, in the nucleus, you have the nucleus, and then you have the electrons, and then you get a coupling between these two degrees of freedom, because you have a charge that is moving, and this generates a dipole, and then this dipole is coupled to the dipole of the nucleus, so to say. Then we analyze what is the role of periodic interactions, how you can use periodic interactions to modulate, to change the properties of the systems, because of course, you can do engineering of the system by introducing impurities, or by changing the structure of the sample, or by inducing pressure. There are many possibilities to engineer the properties of the systems, but alternatively, you can use an approach in which, by shining light, for instance, on these materials, you can induce some interest in physics, and I hope I can convince you that this can be an interesting topic for our future applications, for instance, in nano devices, and people trying to see other possibilities to do the engineering of the properties of these materials. And essentially, at the end, I will show you some recent results about there is now a problem with chiral molecules, the response of chiral molecules like DNA, which although is it's an organic molecule, in principle should not be there should not be any magnetic response if you for instance inject spins in this molecule. Because of the structure, because of the chiral structure of the molecule, you can obtain a polarization of the spins of the outgoing channels. So this is something that was found out like 11 years ago, and people are now still trying to understand what are the underlying mechanisms that give rise to this spin polarization. The spin is connected to different physical systems, and there is like a family of the so-called spin Hall effects. So we learn in undergrad studies the Hall effect when you have particles that are propagating, charged particles moving in a slab of a given material, and then by introducing a perpendicular magnetic field, because of the Lorentz force, the particles will be deflected, and then you can decide which kind of charge carriers, what is the sign of the charge carriers, because the particles are moving in this direction. You introduce perpendicular static magnetic field. Because of the Lorentz force, they get deflected depending on the sign of the charge, and then you measure the transfer voltage. And by measuring this, you will know if it is positive, the charge that you have in your conductor are positive or not. Okay. So there is a family also not related to charge, but also to spin. And then these are the spin Hall effects. And the first one was in 1980 by Hall, was proposed in 1979. There were some recent proposals for quantum spin Hall effect in which the two spin components are propagating along the edges of the sample, but the spin is locked to momentum. So if the spin is up, the particle, let's say, moves in this direction. And if the spin is down, the particle moves in the opposite direction. So there is a spin momentum locking. And this is very important because there are no processes that allow you to flip the spin and then make it propagate in the other direction. So if you, I correct myself. So if you want to have this spin that is originally propagating in this direction, if you want to have it moving in this direction, you have to flip the spin as well. So changing the direction of propagation implies that you also have to change the spin sign, so to say, okay? This has consequences because typically when you, in a transport problem, you change your spin particles and they typically get reflected and they can be reflected with the spin flipping. And when you have this, you have a degradation in your current. And because of this spin momentum locking, this means essentially that you will have a protection in your current. So if you produce a current that is moving in this direction with a given spin, there is no possible way that you will have backscattering. And not having backscattering is important because this reduces the role of impurities. Impurities tend to introduce a momentum change. So if the momentum is changed, spin has also to be changed in order to avoid that you have some kind of dissipative motion in the system. So by this spin momentum locking, what you are obtaining is a protection in the sense that no dissipation is allowed in the system when you have your particles being transported. So far, so good. Please, in case you have any questions, let me know. So there are experimental observations of this phenomenon. And in 2004, this was observed, this quantum spin Hall effect. What they did was to use, they use essentially in the experiment something which is called MOC, is magneto-optical Kerr effect, which is essentially shining light with a given polarization. Circular polarized light will have angular momentum. Angular momentum will get coupled to the spin of the particles in your sample, and then by this idea of the spin Hall effect, you will have one of the spin components, which is displaced to one direction and the other spin component to the other. So you have kind of gate voltage, but spin-dependent gate voltage, so to say. So if you measure the gauge difference, the voltage difference here, you will obtain a finite value, which is interesting because this situation is happening with no net charge propagation, because remember, particles are counter-propagating. So you don't have net transport of charges, but you have a net transport of spins. So this is something which is a different quantity that you are propagating in your samples. So you can separate these two physical quantities by this kind of phenomenon. Okay. So we were talking during some of the talks in this afternoon about symmetries. So symmetries are important because they tell us about which kind of physical coupling terms you can have in a given Hamiltonian. So we know that, for instance, space inversion means that you have like a mirror and observe what happens with the physics when you apply the mirror symmetry to your system and see if the obtained system has physical relevance or is the same as the original one, or if it is different. So if it has the same physical properties, the system is said to be symmetric. If not, we say it is unsymmetric. And this is the way the standard, some of the usual physical quantities of interest change under space inversion. Position gets inverted, of course. Time is not affected. Momentum is inverted, and angular momentum remains invariant under this. Under this kind of symmetry operation. This means that if you have a given, for instance, angular momentum, if you talk about spin, the spin interaction will have to be, if you want to have it space inversion, symmetric, we know that this is coupled. This is orbital degree of freedom. This is the angular momentum. So if you couple these 2 degrees of freedom, and if you wanted to have an inversion, this won't be allowed. So a term which is P times L will not be symmetric under this kind of operation. So if you have P dot L, if you change it, then this will change, and this one will not change. So this will give you, if originally you have P dot L, then you will obtain minus P dot L. This means it's not symmetric, so you obtain something which is physically different from the original problem you have. This was, if you remember, these experiments by Wu that were reflected in this asymmetry between the muons. And this is also connected to chirality in the sense that you have a mirror, and we know that if we want to superimpose our 2 hands in a mirror, the thumbs get out. So this tells you that they are not similar one to the other. So there is a way of differentiating left to right, okay? And this, if you have this kind of systems as compared to these ones in which you can have this kind of good overlapping, then you say this system is non-chiral, and this system is chiral, and this has physical consequences as well. The other kind of symmetries we also are interested in is time reversal symmetry, in which essentially you invert the sense of motion of a movie. So if you have the movie going in the forward time, then you roll it back and see what the physical consequences of that. You know that by the second law of thermodynamics, you can have an arrow time in the sense that you have an increase of entropy. You can connect these two symmetries, so to say. So essentially, this is the way the physical properties change. So now if we have an interaction as in the example before, that is coupling this degree of freedom with this, then by applying time inversion symmetry, you will have an interaction which is invariant under this kind of symmetry. So we see previously it was non-invariant when we apply space inversion, but now if you apply time reversal, you will get something which is invariant. And this has consequences because there is, for continuous symmetries, we know that there is Nether's theorem that tells you that by every continuous symmetry, there is always a conserved quantity. But when you have a discrete symmetry, this is not within the Nether's theorem. There are some consequences in the sense that there are some conservation laws, but it's not essentially covered by Nether's theorem because this is only applied for continuous symmetries, okay? So we know that, for instance, if you have space invariance, space translation invariance, then you have conservation of angular, of linear momentum. Rotational invariance leads you to conservation of angular momentum, and time invariance gives you conservation of energy. And when you have systems which are not strictly invariant under a continuous symmetry, but they are invariant under a discrete symmetry. So you, for instance, let's say you have an array in a one-dimensional system of nucleus. So these are modulated by this guys here at fixed position. So you will obtain a system which is not perfectly invariant, but you have something which is periodic. And this reduced symmetry will allow you to classify your system properties in the sense that by solving the problem of sending the question you want to solve is, what would be the energies allowed for a system in which you inject particles with a given energy, and they are moving in a periodic lattice, one-dimensional lattice. This is the so-called Crony-Penny model, one of the examples that you can solve in the courses of quantum mechanics. And by solving the dynamics, you use Bloch's theorems that tells you what is the consequence of this symmetry in the Hamiltonian. And then what it says is that you can write the solution of this problem in this form, and then obtain the energies from this kind of solutions that have a given exponential behavior plus something which is inheriting the periodicity of your system. When you solve this, then you obtain a classification of the physical properties of the system in the sense that you obtain some forbidden regions. This means for this range of energy values, the system cannot transmit any physical quantity of interest. And depending on the size of this, you can classify your system. If this is forbidden region is very big, then you have an insulator. If it is more or less, you call it semiconductor. If it is zero, it's called a metal. So what we see here is that there is a direct connection between symmetries and physical properties of the system, as we were saying before. You can also use this kind of classification if the periodicity is not in space, but in time. So it's a discrete symmetry in time. For instance, electromagnetic radiation is periodic in time. And there is something equivalent to Bloch's theorem. It's called Floquet's theorem. And in fact, it was studied almost 1 century before Bloch's theorem. But in solid state physics, we learn more about Bloch than Floquet. It's essentially the same idea, but now with the parameter which is giving you the periodicity is time. And then, for instance, in some optical lattices, they can have particles localized in well potentials. They are localized there. And then by shaking the lattice in a given appropriate frequencies, they can induce tunneling phenomena. So essentially what it's telling you this is that the particles are localized. So this is like an insulating phase. And by shaking them, you can produce tunneling between this. So this means you go into a system which is transporting a physical quantity of interest. So there are means to then, by properly tuning the parameters of your perturbation, to induce something which is called photon-assisted transport when you shine light on your system. So this barrier was forbidden the particles to be transmitted. In this, for instance, this model is for double quantum dots. And once you shine light on them, they can hop from this initial system, contact, sorry, to the outgoing system. So what it means is that you can, by shining light appropriately tune the parameters, you can tune them properly. And by photon-assisted transport, you can induce a conducting configuration, a system which was previously insulating. Okay. So we did this by considering what is the Floquet picture. And so what is the consequence? We learn when we learn about Fourier physics that you obtain essentially harmonics in your problem. So you have an original system which is, let's say like this, is uncoupled. And then when you couple the system to electromagnetic perturbation or a time periodic perturbation, what you generate is like kind of replica. These are called sidebands, or we also call them harmonics. So this would be like the +1 harmonic. This will be the -1 harmonic. And the 0 harmonic is your original system. And once you turn on your interaction, depending on the size of the frequency as compared to this bandwidth here, you will have that these harmonics do not couple to each other, or they do, not so much, or they can be very coupled to it. So what this means is that depending on which frequency regime you are in, your system can behave totally different. And solving for the dynamics can be rather complicated depending on which frequency regime you are in. You can induce, let's say you have a system which is on the static configuration is these black lines. They at some point they overlapped at some given point. And once you turn on the interaction, what you induce is that this symmetry, this degeneracy that you have previously here gets broken. And by this, you can induce, as I said before, a system which was conducting can behave as insulating and so on. The spin-orbit interaction depends on which kind of material you have. And of course, this will depend on the electronic configurations of this kind of, of the materials you are dealing with. And in many interesting situations, the particles are not so optically, not so spin active. And in other configurations, they are more spin active when they have, like, for instance, these F electrons or these D electrons, they are more active in spin as compared to those particles who are in the S state, for instance. So you can tune the way of changing this configuration by producing hybridization between the orbitals. And by hybridizing, then you can have a system which is static. And by the hybridization, they can be transporting with, which happens, for instance, in a material like graphene, which is more or less well known now. So these hybridizations are important to be considered when you are modeling your systems, because if there are hybridizations are such that the resulting degree of freedom is not coupled to your interaction, then you will obtain no response of the system. So you first hand had to know if the system should be addressed by the interaction. So somehow some physical intuition needs to be known prior to doing the experiment. So this is the way of trying to suggest the experimentalists which kind of modeling you can use, which kind of parameter regimes you should be focusing in your experiment in order to see something which is different from the standard response of the material. And as I was saying, graphene is one of the typical examples in which you have a honeycomb lattice. So these hexagons are in a perfectly two-dimensional system. So this means, so normally even the thinnest macroscopic sample we have is composed of some given width. So they have like 10 atoms width or whatever. But for graphene, it's exactly 1 atom thick. So this is very special for graphene. And this means that this is a truly two-dimensional system. And of course, because of gravity effects, so what they do in the experiment is that they clamp the sample, and it can happen that the sample gets a bit bent. And of course, then it's no longer strictly 2D, but there are some situations in which they can manage to have it as flat as possible. Like for instance, lying the sample in a given substrate, and they use something which is called boron hexagonal, HBN, in which essentially you have a very flat surface, which is not directly coupling, hybridizing with the orbitals of this material. So you actually have a sample which is perfectly flat, but it's not coupled to the substrate. Then if you have this configuration, then you can see what happens when you shine light on these kind of materials. And on top of that, you can introduce the spin orbit effect that I was telling you about. And this is what we did some years ago, in which we were trying to analyze what is the optical response. So essentially, you have a system in which you shine light and observe what is the outgoing light behaving as compared to what you shine to it. So depending on what you have at the output, you know what you have in the input, you will get information from the behavior of the particles, as I said before, with like this kind of smoke effect. So the optical response of the system will tell you about some of the physical properties of the material you are studying. And depending on which parameter regimes you are, you can have different physical responses, of course. And then this physical quantity, optical conductivity, is also related to this Hall quantities I was telling you about, because one of the main issues about the Hall effect is that in a normal conductor, in a normal material, the conductivity is a continuous function. Sorry, it's a continuous function in the sense that it will only grow or remain flat or decrease. But here it grows in steps. And these steps tells you that for a given range of parameter values, the conductance doesn't change. And then suddenly it jumps to another value. And these jumps are well characterized, and these were the way they initially obtained the physical properties of graphene. So what they did in the original experiment was to measure these steps and show that this was the typical response of a given system, which is quantized. So you have quantized conductance, and this means that there is some kind of protection, as I said before. So the protection, this spin momentum locking, is connected to this quantization of the conductivity. So what we are seeing here is that there are means to connect one quantity even directly or indirectly to the interactions you are introducing. Yes, please. Spin momentum.
This and you said that dissipation still happens, something like this. But this means is the scattering of this.
Okay, maybe I didn't explain myself. Typically, you will have dissipation. So for instance, the Drude model, so essentially what you have is your particle is moving in an environment that is full of impurities, let's say, and depending on the concentration, you will have more or less dissipation, right? This is
Is
expected.
dissipation on the motion, on the angular momentum, or is of particles? As you know,
So
they go out, they flow out from the device.
good question. So what I mean by dissipation in this context is you introduce a given amount of energy, and then some of this kinetic energy, for instance, is transferred, is becoming like excitations of the lattice. So you introduce some heating because of this scattering process. What I mean by spin momentum locking is that even though you can have this scattering to these impurities, there is no possibility to introduce dissipation, because for this you will have to have a density of states that allows you to have, for instance, this spin being flipped and continue moving in this direction. But this is not possible. If the spin is flipped, it has to move in the other direction. So since these two states have the same energy, you will have no energy difference between these two different configurations. And this is the protection that is inherited from this spin momentum locking.
So this is the part exactly what one would like to explore in graphene to have more robust kind of spin systems.
Correctly. So robust in the sense that you reduce the amount of dissipation you can have in your system. Exactly. And this is somehow related to these steps here. And the better they are defined, the better your system is behaving towards this configuration. Of course, we see here that there is some degradation if you change the parameters not appropriately. But what we can get from here is that you can tune the system to be in these special regimes. Okay. Yeah, and you can model this, for instance, also when you have, instead of only a spin orbit interaction and the radiation field, you can have radiation field plus a static magnetic field, as I was telling you before also. So when you have a perpendicular magnetic field, you will have a Hall effect. And the Hall effect in graphene is behaving totally different as compared to a standard electron gas. So in a standard electron gas, the dependence of the energy with magnetic field is in this sense. There are energy levels, discrete energy levels, which are equally spaced. So the Landau levels, or these energy levels in standard two-dimensional electron gases, are equally spaced in each other. This is a consequence of having a quadratic dispersion relation in normal, so p squared divided by 2m. In graphene, the dispersion relation is linear in momentum. And this linearity in momentum can be expressed as you produce these discrete levels, they are not equally spaced. So dependence in a standard electron gases between energy and magnetic field is that they are proportional to each other. In graphene, the energy is proportional to the square root of B. So there is a way to say this material is behaving like graphene and this material is not. So you can discern the physics between these two systems. And of course, because you have this, people are trying to exploit this, because transitions between these guys can be used, for instance, to generate a laser system in which you can tune this energy difference here by the magnetic field, so you will have different frequency responses. But for changing the frequency, you have to change the magnetic field. How about having a given magnetic field and changing the frequencies that you can obtain from this? But you can obtain it here, because since the levels are not equally spaced, you can obtain different transitions. The energy difference between different transitions can be tuned, and this means that you can obtain, by fixing the magnetic field, a different number of frequencies responding from your system. Okay, so people are trying to see if, so this morning, this afternoon, some of you were telling me about autocorrelations. So we also have kind of autocorrelation. So in this context, what we do is that we build a superposition of states And this kind of superpositions is very peculiar because these states are called coherent states in the sense that these are the quantum states. This has been proven by Glauber, that these are the quantum states which behave more classically in the sense that this special superposition in the classical limit, you will obtain essentially the quantities that you observe in a standard system. So this, although this is a quantum system, the representation of a quantum system, you can obtain a semi-classical response. And by changing this parameter, you can have different responses. So you have like these Rabi oscillations in which the system is going back and forth between only two levels. But you can also have some kind of localization effects in which essentially the electrons get packed and propagate like a single structure. So this is more behaving like particle-like behavior propagation, and this is more behaving like wave-like behavior propagation. So you can really see here that you can have a manifestation of the duality of the particles in these two systems. And this can be inferred from this autocorrelation function. We also do it to compare if that graphene is differently behaving as compared to the standard two-dimensional electron gas. And then see what is the optical response. I showed you before the steps for graphene, and we saw that you can have, for instance, this will be like a graphene-like behavior, and you can tune a parameter. In this case is the interplay in a classical in the sense that it's a normal electron gas, and you have you are shining light on this material, plus there are spin orbit interactions in this material. And what you obtain is that you can induce phases in which the conductivity, this is the conductivity, is not changing sign as compared to the standard regime in which you have this normal behavior that we have here, in which the steps are equally spaced. So what it means, what is the meaning from this figure that we have to have, is that by tuning the spin orbit coupling parameter, you can go from a configuration in which you have a standard quantization to a different configuration in which you can only have propagation in a given direction. And this is important for what we were discussing before. So you can say the experimentalist, by fixing these kind of parameters in your problem, you will obtain this conservation we were telling before, okay? So, no, please. So there is a crossover. We don't see like any divergences in the quantities, but we see that there is a crossover in the behavior. But we don't. To be honest, I will not be able to tell you that there is an actual transition. So this is conductivity, transverse conductivity. Like for instance, we were saying particles are propagating in a given direction, and then you look in the transverse direction. So if this is X, and you measure in Y, this will be the, so conductivity is a tensor. So the diagonal terms is telling you are measuring in the directions of the sample, and the off-diagonal terms are telling you that you are measuring perpendicular to the propagation of the particles. And this is proportional. Yes. Yeah. So the diagonal contributions are those that tell you that voltage is in phase with current, and the off-diagonal are those that are telling you that this is 50 degrees of offset from each other. But yes, what you are asking is, it's important to, we have not been able to characterize if this is really a transition in this regime. We were not able to show this. So we only saw this crossover, but this could be like a, maybe a good idea to try to determine whether there is really something happening, that is an underlying mechanism, competition of interactions that allow you to have this kind of phase transition. So the experiments for doing this are really involved. So it's like, this is not my specialty. So this is a slide taken from this group at MIT. They are doing experiments in which they essentially, it's called pump pulse, pump probe pulses in which essentially you use one laser to pump. This means to excite the system. And the other laser is to prove, to obtain information from the system. So essentially you have a setup in which you are using a source to shake the sample, and with the other you say, okay, now give me the response. And these are, I mean, here is a schematic, but this is really something more complicated than this. And at the end, they have a configuration in which they have the sample, and then they can, via this spectrometer, obtain the information, which is essentially reading what is the change in this laser that they are using to probe the system. So it's nice, this kind of configurations, because they can do both things in one step. So this is schematically seen here. So you pump, and with this you probe your sample. Of course, you have to have a detector in order to observe something. These are the kind of results they obtain in Mammoth. Was working with Jarillo in the group at MIT, and they can really see these quantized energy levels that I was telling you before, and these are essentially a manifestation of these different Floquet harmonics that I was telling you about in the schematic picture. So this is seen in experiments, so people can really address these degrees of freedom, and this is also a motivation for trying to continue doing some modeling in this kind of systems. Other systems that we were discussing recently is, so normally organic materials, they don't have, they tend to be semiconducting, so they tend to be insulating more or less. So let's think of plastic, for instance. But in the 2000s, they gave the Nobel Prize to Heger and collaborators because they made a proposal for analyzing the possibility to produce materials which are polymeric, organic polymers, but they can have conductive properties. And this was very interesting because then you could enhance the range of materials that you could use to test these kind of models. And one of the paradigmatic examples were polyacetylene. So here we have the conductivity essentially is like the quantity we were showing before. Typically it is 0, but what they saw there is that there is a region of parameters in which you can have a positive or negative behavior with respect to a given base. This is silver, which is a well-known conductor, and it is, of course, always larger than this one, but asymptotically, they tend to be less different from each other. The main message here is that you can have polymers that get conductive, and this is somehow the way you can understand this. So typically, you have a unit cell of particles which are coupled, and then you have something which is called inside energy and intercell energy. And depending on these parameters being, one of them being 0, you can have at the edges states which are bounded. This means they are insulating because they are bounded to each other, or you can have states which are free. And these are the phases in which you can have conduction in your system. And what is important here is that, as happens with the spin systems, the conductive states are also happening in the boundaries. This means that the materials here can also have topological properties in the sense that they are protected by these kind of symmetries I was telling you about before. So if you, in this kind of system, introduce radiation, then you can have like a system which is in the static regime. You have your original system plus the copies, but they are not connected to each other. And once you turn on your interaction, what you can obtain is this 0 energy modes here. And although I'm not telling you the whole story behind this, these 0 energy modes are very important because they are the ones that are candidates for being the responsible for this topological, also these robust properties of these systems. So this means is that although in the static regime you can obtain no response, no metallic response, by generating this zero energy states, introducing the radiation field, you can have a response which is metallic, essentially. I don't know if you allow me to talk about the 5 more minutes. I told you that there is a bulk response and there is a boundary response. At the edges of the boundary,
Yeah, 10 more minutes. 10 more minutes.
Thank you. So this will be more than enough. So in the bulk, the system can be insulating because as we saw here, if you cut the connections between them, so there will be no way to go from here to here. They get, as I told you before, they are coupled to each other, so they are bounded. But if you cut them the other way around, so you have at the edges, these stairs which are free. So this means that they are free to be accessed by your conducting electrons, for instance. So these zero energies modes are these states which are produced at the boundaries of the sample. This means that if you don't have these zero energy modes, you are in this insulating phase. If you have these zero energy modes, you are in the conducting phase. So this is the underlying message in this figure here. And this is connecting to the edges. And this one here is what happens in the bulk. In the bulk, you will have something which is telling you that the bands are more or less curved. The curvature of the bands is telling you about the velocity of propagation because velocity is related to the curvature of this, the slope of this, the energy dispersion relation between K and E. So when you have something which is approaching flat bands, this means zero velocity. This means that the states are localized. So you can have states which are propagating and states which are localized. And by going from here to here, you only have to properly tune the parameters of the radiation field you are shining on your sample. So it's essentially the same manifestation of the problem I was telling you before, and there are means to quantify the effects by, for instance, analyzing the polarization response of this system. So in this regime where you have this kind of polarization behavior, these oscillations are obviously different from this one here. And then what happens here is that you are in a normal phase, meaning the system is blocked, there is nothing happening. And when you have these kind of oscillations, then you can see that there is conduction, there is something happening. So you can really go from one direction to the other. And to go from this configuration to this other, you only need to have in the appropriate parameter regime. So all in all, what I want to say is that you can really make in the engineering of this kind of systems, and the last example of this is with DNA. So this experiment in 2011, I don't know if this question, no? So in 2011, they made this experiment with DNA. So they have different samples of DNA, single-stranded and double-stranded. And what they did was to China, so they threw some electrons, unpolarized. When I say unpolarized, I'm referring to spin. So you send spins that are either plus or minus, so in a combination of them in such a way that you don't have a net magnetization in your current. And then at the end, what they observe is that there is a possibility to induce some polarization in this in the output. And what also they found is that if they did with single-stranded DNA, there was no response, and with double-stranded there was response. So there is one characteristic that is associated to the features of the sample you are using, and they also analyze what happens when you change the polarization of the light you are using to read out your quantities. And what they saw is that with circular polarization, you obtain this kind of response, which is, with linear polarization, you obtain this kind of response. With left polarized light, you obtain this and this. And if we remember what is the difference between circularly and linearly polarized light, this one is not carrying any angular moment. Linear, this one here. Linearly polarized light is not carrying angular momentum. whereas circularly polarized does have angular momentum. So you would expect a stronger response because you are introducing angular momentum with your circularly polarized light. But what they saw is that when you shine light, which is not non-polarized, so there is nothing that is, how do you say, like, in principle, should not be coupling to the spin degree of freedom, you obtain the largest response in your system. And they were like, shocked, what is going on here? And the issue that they used different kind of polarizations was to say, this is not only the light, so it's not because you are introducing angular momentum. Here you will not be surprised, but this is surprising. And what they saw is that it's not only in double standard, but also with linear polarization. So what they did was the obvious, to change the sample. So now you don't have a molecule which is chiral. So instead of having something which has a directionality, you have something which is non-directional, so non-chiral. And because of this small change, they noticed that the response of the spin was related more to the form of the molecule you were using. And if we remember in basic courses of optical activity, I don't know if you did this experiment in which you have sugar, some water, sugar in water, and a given concentration of sugar. If you shine light in that sample, at the output, you will obtain a light which is not in the same direction of polarization. So what the sugar does is that it rotates the angle of polarization of the light. So this is called an optically active sample. And this is connected to the chirality of the molecule of sugar that couples to the polarization of light. So you can have a coupling between the spin of the light with the geometry of the molecule. So if it is chiral, you obtain optical activity. If it is non-chiral, the outgoing light will be essentially the same as you shine on it. So there is a way to introduce angular momentum in the sample that is not related to light, but related to the geometry of the molecule. They saw the experiments of this. They were reporting experiments recently on this. There is still a debate of what is the role of, for instance, electron-electron interactions. Sorry. For instance, here, there are no spin models like, I have not seen papers in which they try to interpret this polarization by using like Ising model or Heisenberg spin chains. I have not seen something connected to that. So I don't know if that is something that it might be like connecting what we are doing to what you are doing related to spin systems. But what we did was to see what is the role of spin orbit in these kind of systems. And essentially, some colleagues, what they show is that it is very important to have not only the chirality of the molecule, but also a spin orbit that can couple the orbit of the particles that are moving in the chiral molecule and the spin of the moving particles. And if you on this DNA shines some light, essentially, as you expect, this is why I'm telling you that it is interesting to do that. There is this behavior when there is no light, and there is this behavior when you have light of a given polarization, and this is the response of one of the spin components, and this is the response of the other spin component. So all in all, what is telling us this picture, with no light, you have a spin degenerate states. By shining light, then you have two spin components that behave differently in energy. So you break the energy degeneracy, and this is a means of telling you that you could have a response that is dependent on this. And this indeed, we analyzing the energy spectrum, so you can have energy separated states, meaning why is important now here to have energy separated states? Because you want to have one spin component to be singled out from the other. So you can say, this is a spin up and the other one is a spin down, or the other way around. What is important is that you can differentiate one spin component from the other. Whereas when you don't have the radiation field, there is no means to say, this is a spin up and this is a spin down. This is the message. So I think this is the outlook. With this, I'm almost finished. So now we are analyzing some materials which are interesting for us in the sense that I was telling you about normal two-dimensional electron gases with a dispersion relation in which you have momentum is quadratic to energy. So energy is momentum squared. In graphene, you have energy is linear in momentum. But in this kind of materials, which are called symmetric materials, you can have one direction of propagation in which it is behaving like p squared, and in the other direction is behaving linear. And these materials are important because then you can have like a tuning and an anisotropy of the properties. And this has been experimentally observed. So what they do is that they have a material and they dope the material and they obtain this kind of energy landscape. And this tells you that you can find maybe a study to analyze the crossover we were discussing before between linear and quadratic behavior in the energy spectrum. And this is something we are doing now. So there are these are preliminary results. I just wanted to show you a beautiful picture, but we are still trying to understand what is going on here. So this is an energy momentum relation with light and without light, but we are still trying to understand what is going on here. And also measuring some polarization effects. We want to see what is going on. These are ongoing work. With this picture, what I want to say is that there is a whole range of parameters that you can address in this kind of systems, whether the probe, so the light that you shine is chiral or achiral, so linearly polarized, circularly polarized, whether the matter is achiral or chiral, for instance, a normal molecule or DNA or sugar, or the interaction between the sample and the environment is incoherent or coherent. So with this landscape, you can really play in your parameters in such a way that see what you can do in order to engineer the properties of the system. So this is the take-home messages. So I think I will stop here, and I will thank you again for your patience, and I will be glad to respond to any questions if there are any. Thank you very much.
Thank you, Alex, for the nice talk. So now we will take some questions. So if anyone have any questions.
Yes.
How do you simulate these things? So I think you told me that it's a tight binding models.
Yeah, thank you.
But then the radiation and field and so on.
So this depends on what you say is very important, because this depends on which level of accuracy you want to achieve. So of course there are ab initio models in which essentially by putting all the ingredients and not a priori assessment, you just simply put all the ingredients and see how the system behaves by ab initio means that. Also, there is DFT, in which what they have is that they try to find which kind of configuration is the more stable for determining parameters, in the sense that, to determine the parameters, essentially what you obtain is a system in which you change the interaction among the particles by a functional of the density, the particle density. This is density functional theory. But there is an extension of this static density functional theory to time-dependent problems. They do something like this. But for this, you need something we don't have, which is large clusters of in which you can do large computations. So for this, there are packages that are more or less, the licenses are expensive. So we work with what we have. So as I said before, so you have ab initio, then you can, I would say there is DFT, then you have tight binding, and tight binding parameters are fitted from the DFT ones. And then from the tight binding, you obtain your whole spectrum, approximated whole spectrum. And then what we do is to fix certain symmetry points and analyze the physics around these symmetry points. And why is important this? Because in many experimental situations, these symmetry points are the most relevant for the experiment. So we try to do calculations which are somehow connected to what experimentalists can address in this case. Of course, they can address more details than what we do, but in these approximations, we can say something which is more or less physically appealing, so the mechanisms can be understood, because we also try to find analytical modeling, so to try to find, in principle, exact, although there are not exact, but approximate solutions. And then is what we do, so a simplistic modeling, but trying to keep the main ingredients which are relevant for the experiment.
More questions?
Components of spin happening by tuning parameters. Uh, so this is the same particle, but just you have. No, this is not the case. I think there's still a superposition between two positive and negative.
There's no. So these are single particle models.
Mm.
Maybe if you want to
So
introduce.
you have one particle moving that way with this, and you have another particle, but it's not basically a superposition. Superpositions moving separately, following this angular momentum locking.
Okay, so maybe if I understand correctly, is to what I say angular momentum and spin angular momentum looking what I'm talking about. This is maybe the question?
Yes. In that regard, also, I mean, if you what I said is if you change parameters, then you, for example, the last one of the last slides you show us, you have this symmetry breaking between when you don't recognize whether you have positive or negative spin direction, let's say,
Yes.
and then you split this thing. But each one happening in one of the minimums is not the same particles. So the particles with the spin positive are in the blue, let's say, and the other ones in the red one. This is the case, right?
Yeah. So if the experiment tells you that this is the response, then you are sure that you are having this particle with the spin plus or spin up. However, if the experiment is with the same particle and you obtain this result, and then this is telling you in which spin state is this particle. A natural extension of this is when you have two spins that you want to address, and then you want to see two particle response, right? So in that case, there are different possibilities. One of them is to introduce, for instance, dipole-dipole interactions. This will allow you to address a system in which at least there is a binary configuration of particles that you are not treating independently from each other. But there is also, we were discussing about this, there is also a means to not have direct interaction between the particles, but particles in this context, they move in a lattice. And in this lattice, you can have also vibrations, phonons, for instance. So you can couple two particles, which are in principle independent, with the lattice vibrations. And when you have something like this is called an exciton. You can also have electrons and hole coupled. So an electron, a positively, negatively charged particle, in a hole, a positively charged particle, which get coupled via the bifurcation, for instance, or also via phonons. And then, although the particles are not directly interacting, they have an interaction which is mediating the coupling between them. So this is no longer
entanglement between the two. Entanglement between the two particles, or not necessarily.
Oh,
would that induce entanglement? That's
this is something we were also discussing, because there are some proposals to have non-interacting particles which get entangled. But so at the discussion, so when we were having this discussion, I have to be honest, because there is no a natural mean to have particles which are non-interacting and get entangled. So unless you have something which is somehow mediating among them, you will not get a means to connect them. So in principle, when these particles are correlated, so you obtain something which is called a quasi-particle, which is two particles connected via the lattice vibration. So it's no longer an electron, no longer a a hole, but something which is a composition of all of them. But still, you can have like singlet states or triplet states depending on which energy regime you are in. Yeah. So, of course, what is the natural extension of this? The most basic to introduce something which couples two particles. So instead of analyzing a single particle model, something in which you really have interaction among the particles. But if you saw the formulation, the particles are interacting with the radiation field, with the lattice vibrations, with the gate voltages, but not with each other. So this is a next step to be considered, of course. Because please correct me, when you don't have direct interactions among the particles, you cannot have phase transitions, I think. I think you need interactions to have phase out transitions, no? Because, for instance, if you have a spin system, like in the IC model, you have the spin interaction plus the coupling to a magnetic field, and then you have like a critical value of the magnetic field for which you can have a transition, is something like that. I'm totally ignorant in this. I'm trying to find like a more or less suitable, reasonable answer to your question. But to be honest,
Nice.
this is something I have not done so far. It's always single particles interaction to the environment.
Okay, is another question.
Yeah. No, please.
I once heard. I'm not. I haven't seen too much about graphene, but one friend once told me that there was this superconducting regimes of this guy, and then this guy is doing. He's on this quantum field theories working, and he was interested in this because trying to get, for example, electrodynamics in two-dimensional stuff, it seems like these things happen. No?
Yeah.
Have you seen something like that, or something related with this all symmetries, reality, and this?
So first, I have to say that for this for instance, these superconducting phases they were observing. In fact, it was in this Harillo group I was telling you with the schematic picture of the experiment. So you need to have bilayer graphene. So these four models for single layer. And what they did at that time is that typically the layers tend to organize into specific configurations. And what they did is to change a bit the system and say that they rotate one of the layers with respect to the other. So this one was fixed and the other was rotated. A small angle, one degree. And when they analyzed the response, so they made this spectrometer pump probe sample, what they observed that they were some flat bands, meaning zero velocity space. Zero velocity in their interpretation means heavy fermions, so fermions which are very massive and they don't move. And heavy fermions are connected to superconducting phases. So it was the way they could connect their results to superconducting. And not only that, they make a temperature study, temperature dependent study, and they found something which was behaving like flat, and then at some point having a different from zero value. So this is the typical behavior of a normal superconductor. So there is a critical temperature below which the system is not changing properties, and there is up to this critical property, the system is not perfectly conducting, so to say.
Yeah.
Yeah. So this was an indirect way of having a superconductor in a system which is not expected to be superconducting. And this was why this system was so, this experiment was so in the media.
Yeah. Okay. Thank you.
So the physics is very beautiful, and as you mentioned, they can do high energy physics, so to say, quotation marks, in low budget with low budgets. Although this is not so cheap, but compared to LHC or something like that, is much cheaper. Yeah.
Okay, any other questions? So if there is no question, I just have one. Okay, a quick one, maybe not so intelligent question. So when you mean by the two in non-interacting particle and entanglement between two non-interacting particle via lattice vibration, so actually do you want to mean by composite fermion kind of thing?
Oh, this is a good question because if I remember correctly, what you do here is that, sorry, you have the states of one particle,
Yeah.
you have the states of the other particle, and now you build proto states of these two non-interacting particles. And then what you obtain is at the output is a combination of all the possibilities. And then what they do in the experiment is to see what is the weight of each of these different components that you in principle would have in the most general
So
scenario.
can I say that this is basically two interacting composite fermion?
Interacting via these lattice vibrations, yeah.
It's a composite fermion, but interacting, right?
Yes, yes. So it's like more or less so this analogy is not perfect, but it's more or less what you have in superconductivity. So you have particles which are coupled via this superconducting back.
Or just like fractional Hall effect.
Yeah, exactly. But in there, for instance, in fractional Hall effect, you do need interaction among the particles. So these are no longer independent particles. So you do need to have interactions to obtain the fractionality.
Okay, so if there is no more questions, then let us
Thank you very much. Thank you for the nice questions.
The speaker once more.
Yes.
Thank you, Alex, for this nice talk and very nice explanations. Thank you once more.
Thank you.
So we will close the session here. Our next speaker will be Dr. Ann Cross, and that will be in 2 weeks. So this is a bi-weekly seminar, so that will be in 2 weeks. So she is a home speaker, so she will be